I'm Adolph Oliver, and to start our study of algebra, it's appropriate to say a little bit about where the algebra came from. The beginnings of it can be traced all the way back to Babylonian times, but the real development of algebra was during the Arabic Golden Age in the 9th century. You can see this in the name algebra. The letters AL are very common letters found in many Arabic names. During this time, Europe was using primarily geometric methods of solution. The algebra was unknown there. It wasn't until the Renaissance that the algebra became known in Western Europe, and since then it's become part of the heritage which is passed down to us today. Well, the first thing we want to talk about is the difference between basic math and the algebra. And the key here is that in basic math you have all the numbers, but in algebra you do not know some of the numbers, so we replace them by letters until we can figure out what their numeric value is. This idea of being able to use other information about some unknown value and then use that information to figure out what it is what the real power of algebra is, and using these symbols helps us to do that. Now, as we said, you may not know what the actual number is, but if you know something about it, like for instance, if we take 3 times a number and add 4 to it, the total is 10, then what we can do is write that as an algebraic equation. Here we have 3 times some number plus 4 equals 10. Well, of course, this is a very simple equation which you can look at and figure out the value in your head. We'll be talking more about equations in a little while here. But first, let's point out that these letters that stand for the unknown values, like the X here, are known as variables. The idea is simply this. We allow these to vary until we hit the value that solves the equation. Common letters used for variables are X, Y, and Z, although any letters can be used. Now, sometimes we also know numbers in an equation, but they have long values. Instead of writing a long number in an equation, it is easier to use a letter to stand for it. Well, as an example of this, the formula for the circumference of a circle, C equals pi times the diameter. Remember that the distance all the way around the outside of a circle is known as its circumference, and a line through the center from one end to the other is the diameter. Well, the Greeks figured out that there was a constant proportion between these two, and kind of in response to that, to this day, we use the Greek letter pi to represent what this value is. Now, we'll study pi later on in the algebra. It's an example of what we'll call an irrational number. Its value goes on forever, and if we were to write down what it was to say about 7 decimal places, this would be its value right here. Well, this is a pretty long number, and it's much easier in an equation like this one we have up here, C equals pi times d, just to put the pi in, and folks are familiar that pi stands for this value. So that's the idea. Numbers that stand or that are long and that we use symbols for in equations are called constants. Pi is an example of this. It's a value that does not change, in contrast to a variable, which is one we allow to change until we get the correct answer. Common letters used for constants are letters toward the beginning of the alphabet, A, B, and C, and letters of the Greek alphabet, for instance. So here's the idea once again. What we have are variables which vary, and those are values which we're solving for. And then we have constants, which are plain numbers that do not change, but it's just easier to use them in the equation instead of writing out this long number. Well, one of the things that we've been talking about so far here has been equations, and there's a very important distinction we need to make right to begin with. The difference between what is known as an expression versus what is known as an equation. Here's the key. An equation has two sides. Now, what separates the sides? The equal sign. Some folks have the idea that there's an equal sign that's automatically an equation. This is not true. It's only an equation if there's something on both sides of the equal sign. So since this has something in both sides, it definitely is an equation. Now, that's in contrast to what's known as an expression. An expression is just one-sided. Again, we see an equal sign here, but we only have one side. There's nothing on the right, and you can't put a zero or anything else like that in there, because if you did, you'd be making up your own equation. A zero is a perfectly good number, like -1 or +1. So let's look at this again. An expression versus an equation. An equation has two sides, which makes it act like a balance scale. That means that we can add the same to both sides, we can subtract the same from both sides, even multiply or divide the same on both sides. All of those are operations which we'll use to solve equations like this later on. But for the moment, what we're going to say is, since it acts like a balance scale, what we're seeking is the value of the variable x, which makes the two sides balance. And so this variable, once we figure it out, will be the solution of the equation. Whereas on the other hand, an expression like this down here, which doesn't have another side, so it's not a balance scale, you can't do any of those methods. It's impossible to figure out what the value of x is in an expression, but you can do this. You can turn around and substitute a value in and come up with its numeric value. So let's point this out again. What we've been saying is simply this, okay? An equation acts like a balance scale and can be solved for the value that balances it. This is known as a solution. What we'll do in the future, I'll just give you a quick little look at this. Many of you know this already. We'll get rid of this +4 by subtracting 4 on both sides. That'll knock out the +4. I'll end up with 3x equals 6. Now I can divide both sides by the same thing, namely 3. That cancels out the 3's, and we end up with x equals 6 divided by 3, or x equals 2. This is a simple enough equation that you could have looked at this and figured out that x had to be 2 to begin with in your head. But of course, the real power of algebra is not in solving simple equations like this, but in solving much more complex things, and we'll see those as we go along in the course. Now, the other hand, what we said earlier is about an expression cannot be solved as it is not a balance scale. But it can be evaluated if someone tells you what numeric value to use for the variable. So let's say someone tells us to use x equals 5 in this one-sided expression. Well, what we're going to do is build up some techniques here which are going to see us through much more complicated problems later on. What I suggest you do is this. Where the variable exists, and see x right here, make a hole with the set of parens for that x. Write anything else that's there exactly like it is. In front of the x was the 3, so we write 3 in front of this set of parens. And behind it, the plus and the 4. Now, here's what the parens does. It preserves any operations like powers or multiplication so that we don't lose track of these. And in more complicated problems, this becomes very important. Well, what we're supposed to plug into this hole is a value they told us up here, namely x equals 5. Once we've done that, notice what you've got now. You're back in basic math. You've got all the numbers. We simply apply the order of operations, which tells us we have to multiply before we add. So we go 3 times 5, which is 15. Copy down anything that we haven't used yet, like the +4. Now there's only one thing left to do, so if you only have one thing to do, you do it. 15 plus 4, that gives us 19, and that's the value of the expression when x equals 5. Now, if we use some other value for x, we'd have gotten some other value for the expression down here. So, one-sided expressions, you can plug a value in and evaluate them, but two-sided equations, we can turn around and solve those and come up with the value for the variable that balances it, because of course an equation acts like a balance scale. Well, this first section we're going to be dealing primarily with these expressions, one-sided things, and we're going to be given values to plug in for the variables. So let's get some practice at doing some of these. Okay, here comes the first one we're going to look at. We have 6x, the 6 and the x next to each other means 6 times x, plus y. This is one-sided. I could put an equal sign here, but since there's nothing given on the right side to begin with, this is still an expression. The only thing we can do is plug in the values that were given for x and y. Once again, make a hole for each one of these. Here's a hole for the x. What was in front of the x was the 6. Then we have a plus sign, and then after that comes the y, and I make a hole for the y. Now, in simple problems like this, you could probably get this correct without using the holes here that I'm generating, but they preserve what's going on. Notice the 6 next to the parens means multiply, just like the 6 next to the x does. Okay, the next thing is very carefully get the correct values in each of the holes. This first hole right here is the x. Our x is supposed to be 5, so we put 5 in it. This second hole here represents the y. Our y is supposed to be 6, so we put 6 in that. Now you're back in basic math. We have to do the multiply before the add. 6 times 5 is 30. Copy down all the parts that you haven't used. They're just plus in front of this 6, so this is just plus 6. And of course, once we get down to just one thing left to do, you don't need the order of operations. You just do that one thing. 30 plus 6, the value of this expression is 36 when we plug in these two values that were given. Okay, well, we can have things that are a little bit more drawn out. Here, y plus x minus 4. Well, again, as always, we could put an equal sign here, but since there's nothing on the right, this is an expression, so all we can do is substitute in for these values. So, again, make holes for the variables. Plug in the values once you get everything set. Now, let me point out to you what we've done here. We've just taken the original expression up here, rewritten it, but every place we've seen a variable, we've made a hole with a set of parens. Now, once you've got everything else copied down exactly like it is, then turn around and carefully get the variables in the right place. Now, be careful. This first hole right here is the value for y. What's y? Y is 1. So we put 1 in there. The second hole is for the variable x. What was x given to us as? 4. Okay, here we are. We're back in basic math. We've got an add and a subtract. The order of operations says work from left to right. So the first thing we'll do is we'll add these two. 1 plus 4 gives me 5. And then we write down everything else we haven't used yet. The minus 4. 5 minus 4 now just gives me the final value 1. So that's the value of our initial expression, plugging these values in for x and y. Okay, well, we can have more than 2 letters. Actually, there's no limit to how many you can have, but here's an example where we've got 3 of them. So, okay, once again, make holes for all your variables. Here's a hole for the x, then I have the plus sign. Here comes a hole for the z. Okay, and then I have the minus sign, and lastly, a hole for the y. So again, I've just taken the original expression, rewritten it, made a hole for each of the variables, and now you simply plug in the values, but you must be careful to get everything in the correct place. So, this first hole is for x. My x is supposed to be 1. The second hole is for z. Okay, well, what's z supposed to be? Z is supposed to be 5, so be careful when you put these in. The last hole here is the one that matches y. My y is supposed to be 1, so there I am. Now, just like our last problem, All we're doing is adding and subtracting here. They're of the same level of importance in the order of operations. So we work from left to right. The first thing we do, 1 plus 5 gives me 6. And I copy down what hasn't been used. We're just subtracting the 1 here. And 6 minus 1, of course, equals 5. So there is the value of our expression. Now, it is not uncommon to have fractions in these. Here's an example. Okay, we've got two variables to plug in, a and b. Again, this is an expression. It's one-sided. So what I'm going to do is make a hole for the a. Here it is. There's a hole for the a. The a is being divided by 6. So I turn around and do the division sign and the 6. This is basically a big fraction here, but fractions indicate division. And then we're supposed to add to that the value for b, so I make a hole for b. Okay, now we're all set to plug in our values. Again, be careful, make sure you get the right ones in the right spot. The a is supposed to be 6. Okay, we put it in the hole matching the a. The b over here is supposed to be 4, so we put it in its hole. Now, one of the things about fractions is you always have to reduce them, and even by the order of operations, if you thought of this as a division, you would have to do division before addition anyway. So 6 over 6 we know equals 1. So now we copy down the things that we have left here, the plus 4, and of course we're down to just doing one thing, so go ahead and do it. 1 plus 4 equals 5. 5 is the value of our original expression up here when we plugged in a equals 6 and b equals 4. Now, the fraction can be more complicated. Let's look at the next example here. We have a fraction again, but there are two variables being added in the numerator. Now, we mentioned just recently that, of course, one of the standing things you always have to do with a fraction, in the final answer, you always have to reduce it. But you cannot reduce a fraction until you get a single number upstairs and a single number downstairs. Well, we got the single number downstairs. There's no problem with that. But what we have to do is figure out what the upstairs is. Okay, once again, I'm going to make a hole for each of my variables. Here's a hole for the a, and then the plus sign, and a hole for the b. And then we turn around and we're going to divide the whole thing by 4. Now, I mistakenly put b in there. I want that to be a hole where I'm going to put the number in, so let me cross that b out. Here we go. And now, what are we supposed to put in the first hole for a? A 1. What do we put in the second hole for b? Well, not the letter b like I did by mistake. We put in 3. So let me just kind of squeeze that in right here. Okay, well, what do we have now? I'll scoot the page over a little bit here so we can write it down. We have to get a single number upstairs before we can reduce this fraction, so that means we have to add these guys together first. 1 plus 3, remember that's a 3, equals 4. Well, downstairs we still have the 4, and of course what's 4 over 4 equal? It equals 1. So there is the value of our expression when we plugged in a equals 1 and b equals 3. Remember, you cannot reduce the fraction until you get a single number both top and bottom. We had a single number bottom to begin with, so we had to add these guys together first. Then we can turn around and reduce the fraction. Well, the next thing that shows up is we can have situations where we've got some more parens involved. Let's take a look at this example right here and see what's going on. We have 5 minus, and in parens, b minus a. Okay, here's what we're going to do. As always, I'm going to make a hole for each of the variables. Here's a hole for my b. I've got a minus sign between it and the hole for the a. Here that is. Now, I've replaced the b and the a with their holes. I've got the minus sign in between. But I have to write down all the other things. You see this large paren to the left of the b? Here it is. The large paren to the right of the a? Here it is. And of course out in front a minus sign and a 5 even before that. Okay, well, we're all set. This guide I've written down here is exactly like this. The only difference is what we've done is I've replaced the B with its hole and the A with its hole. Now, carefully get the correct values in. Notice the first hole is B, so B is 3. Put the 3 right here. The second hole is A is 1, so put the 1 right here. Now, in the order of operations, it says do things in parens first. Notice these little parens that we've been putting in here, like the one for the B and the one for the A, they've got single numbers inside of them. There's nothing to be done inside. Once you get what's inside parens down to a single number, you've done everything you can. Well, these were given this way. But you see this larger set of parens here? This one right here has something to be done inside. This is not a single number in this big set of parens. So that means we have to do that first. The order of operations, you always do things in parens before you multiply, divide, add, or subtract. Well, once we see that we have to do this inside parens, then we just simply look at what's inside the parens right here and do that operation. And there's only one thing to do, so let's go ahead and do it. 3 minus 1 gives me 2. Okay, so what's inside that big set of parens? Here's my left and right big set. It's 2. Turn around and copy all the guys down that haven't been used. The minus from in front and the 5 from in front. Okay, well, now there's only one operation left to be done. 5 minus 2 simply gives me 3. So the final value of our expression turns out to be 3. So remember, if you've got other parens in here, copy them in. They're part of the problem, just like the minus and the 5. Now, the next thing we can have, of course, are some exponents in these guys. So let's take a look at the situation where we got something like this going on. Here we are. This expression, and remember again, we can put an equal sign up here. That does not make it an equation because there's nothing on the right. The y next to the parens means multiply. And inside the parens, we've got x squared. Okay, well, here we go. We're going to make a hole for each of the variables ourselves. The y gets replaced with a set of parens. Then the x gets replaced with a set of parens. Here it is. But now notice, the x up here is squared, so that means we've got to square the parens that we made for the x. We've got to preserve all the other operations. And the other thing, the x squared is enclosed in a larger set of parens. Here it is. Here's the left one, and here's the right one. So look carefully again. What we've done is made a hole for the y. We have the larger parens on either side. We've made a hole for the x. Since the x was squared, we had to square this hole. Okay, now carefully get everybody in the right spot. The first hole here is y, so we plug 4 in. Here it is. The second hole inside here is for x. X is supposed to be 2. Now, by the order of operations, we have to do anything that's inside parens first. Notice, of course, the little parens with the 4 has a single number. There's nothing to do inside there. The little parens here with the 2 inside, there's nothing to do inside that. But the larger set of parens here, we have 2 squared inside of it. That's not a single number yet. We have to do that power. So let's go ahead and do that operation. 2 squared is 2 times 2, which is 4. So now we know that the value inside the larger parens here is 4. These parens I wrote down here are the larger ones. Here they are. Now, don't forget the 4 inside the parens in front. Okay, you can't leave off anything that you haven't used or you won't be getting the correct answer. So all we did here, following the order of operations, since there wasn't a single value in this, we had to do 2 squared. We got the 4. We copied down the 4 that was in front. Now, of course, the only thing left, we've got 2 4s next to each other in parens. That means multiply. So our final answer here is 16. Okay, let's contrast that with one last example here. Here we have a larger set of parens that's being squared, and inside we have y minus x. Well, once again, what I'm going to do is make individual holes for both the y and the x. Here they are. There's a minus sign in between them. Then we have the larger parens on either side. There's the left, here's the right. And then, of course, remember the larger parens here were being squared, so we have to have the square out here as well. Now, carefully put in the values. The first hole is y, which is 3. The second hole is x, which is 1. Now, remember your order of operations. You have to do anything in parentheses first, any of the grouping symbols. The 3 and the 1 inside here are already single numbers inside, so there's nothing to do inside them. But we do have this big set of parens right here, and this is not a single number inside it. So what we have to do to begin with is subtract 3 minus 1, which gives me 2. Now, that's still enclosed in the big set of parens, and of course why we need to keep that, the 2 out here is squaring the whole parens. And so we got the big parens down to a single number, did what was in the parens first. Now, after that, we drop down to powers. Well, the power is the only thing left to do, so since it's the only thing left to do, we do it. 2 squared equals 4. Okay, so there it is. The value of our expression right here turns out to be 4.